list, but I think I also prepared these slides with students in mind, so if it's a bit elementary, I hope you forgive the level of exposition. So that's why I started out with a very few elementary slides reminding you what Diophantine equations are. So we'll be interested in polynomial equations, like for example with integral coefficients. And when we refer to such an equation as Diophantine, I'm sure you know, it's because we're interested in solutions with coordinates in usually rather small rings, like the rationals, the integers, or algebraic number fields, rings of algebraic integers in number fields, or we also allow a few primes to be inverted and look at solutions inside rings of S integers. So these are the typical Diophantine problems. So when you get very general about these things, you might say that more generally the Diophantine geometry is the study of maps between schemes. Well, these are that are of finite type. So this is a very general formulation, but which is reasonable to adopt when you're trying to put yourself into a suitably flexible setting. So if we're given, so this is just notation, but when you're given a ring, we'll denote by X with bracket A the set of A solutions to the equation, solutions with entries in A. So this view over here is of course very well known now, it's very old due to Grothendieck at least, that we should try to study such solution sets by thinking of them as maps between spaces. So this is the view that was more or less at the foundations of scheme theory. So this viewpoint informs arithmetic geometry as a whole, and we're supposed to be able to study, use geometric intuition to solve equations. And sometimes it works and sometimes it doesn't. But the difficulty is that if we look at sets like rational solutions or integral solutions and so forth, in spite of whatever, so for example, if you have, I'll remind you, if you have, say, a variety defined over Q, so you're viewing a rational point as just being a section of a fibration, and this is philosophically a useful view, but it's very hard still to think about this in a geometric way, in spite of Grothendieck's foundations. So a lot of the actual hard work involves starting in this setting and fleshing this out so that you can really use it to get theorems. Now, so I'll remind you, for example, that even for a very simple equation like this, right, we know that the rational solution set is finite. Right? But even for this family, we really don't know how to compute this. Right? For all we know, if I ask you for the solutions, complete solution set, as I vary A, B, and C, right? For all we know, this could be an uncomputable problem. Right? This is still, it's embarrassingly unresolved questions like this. And so, as I was saying, the really non-trivial part of Diophantine geometry consists of starting from this idea, then enriching the sparse geometry in some manner. So the usual, very classical approach to enriching the geometry is putting the rational solutions inside solutions with more evident geometric structure, like inside the real solutions. I already gave in the popular lecture this morning, if you're studying elliptic curves, it's very common to draw this picture of the real solutions and draw lines in order to study rational solutions and say something about it. So the reals is one thing, but also classically we know that we also use the p-adics. And in fact, so this also, the p-adic solution set of equation also is usually more evidently geometric. So both of these have the advantage that you can do some kind of analysis, analytic geometry in addition to the scheme theory. that underlies the original definition. So, I mentioned earlier already that this is a very classical approach, that we try to study the set of rational solutions by putting it inside all the completions at once. So these are the adelic points. Right? So, by the way, normally you put a little prime here or something to indicate that actually the target lies inside some restricted direct product. But in any case, this is a very classical approach to studying rational solutions. Even before scheme theory, that we should try to use all the completions at once. Or there might be also S-integral refinements of this sort. If you're interested in specific integral solutions for affine equations, you might just use some of the primes that allow denominators in some of the primes, and then request that require most of them to be integral and so forth. So this is, as I repeat, is a classical approach. So I'll remind you what people do with this. So the most classical case, in some sense, is this case of the Koenig equation, ax squared plus by squared equals c. So this is the kind of equation you can deal with in an undergraduate course. And as we know, even here, sometimes you have obvious rational solutions, and sometimes there are no rational solutions. The way we think about one obvious application of this embedding into completions is that in this case there are no rational solutions because there are no real solutions, right? Or if you look at an equation like this, there are no rational solutions again. But in this case, it's actually because there are no Q2 solutions inside the two-eddy completion. Yeah? So this is one way one uses these completions to rule out the existence of solutions by showing that there are no solutions even inside this bigger field. So this is a classical story. And for conics, this, as you know, this is very satisfactory because there's the theorem of Hasse-Minkowski. Somebody told me that this is not the Hasse-Minkowski theorem. That is, the Hasse-Minkowski theorem is when you have many variables, but this with just two variables, I guess, was known before that. But I don't know. I don't remember the precise details. But anyways, I'll call it all of these the Hasse-Minkowski theorem. It says that for these Koenig equations, there is a rational solution if and only if it has a solution in every completion. Yeah? So, as you know, the only if is clear, right? But the if part is actually interesting in non-trivial number theory. Yeah? And it takes some proof. And it involves actually class field theory as well at some in some rudimentary form. Say quadratic reciprocity or Hilbert reciprocity. Furthermore, you know that as far as the existence of solutions inside these completions are concerned, there's even a straightforward algorithm for determining this, right? That, so this is the harmonious part of this theory. So this theorem says that you only need to check locally at all the completion, and for each of the completion, actually, it's possible to deterministically check whether or not there are solutions. I'm not going to write it down for you, but there's this, you can express everything in terms of Hilbert symbols, which are readily computable. And we of course, also it's important to note that you're supposed to check for solutions in all QV, but you only need to check that finite collection over there. The rest are automatic. So this is the most classical case. But if you're like me, or if you're like any undergraduate student, normally when you see this equation, this theorem, there's something unsatisfactory about it. And that's what I want to talk about in this lecture. The unsatisfactory part is that the theorem doesn't tell you anything about how the rational solutions sit inside the local solutions. It just tells you, gives you various statements about implication about existence, right? Now, to some extent, this is enough if you're really just interested in finding solutions. Because why? Once the theorem guarantees the existence of a solution, you can just search until you find it, of course, just by heights in increasing order of height, you try all rational numbers and you find it. And of course, there are more refined versions of that algorithms as well, using continued fractions. So, in some ways, the existence theorem, you could say, is the main thing. And for conics, you also know that if once you find one solution, you can parameterize the full solution set using geometry. Nevertheless, the theorem by itself is very curious in the sense that it doesn't really tell you the relation between the local and global solutions. So for example, of course, if you just take a collection of local solutions, it's almost never going to be actually coming from a global solution. So what does one do about this situation? And in some sense, so this is a problem that I've been worrying about for many years, starting from this elementary case. So this is the question. Now, interestingly, in some sense, there is a solution to this question. There is an answer to this problem, or a solution to this problem, answer to this question. So how does that go? Well, this is actually the answer provided by class field theory. So in order to describe this, let me simplify a little bit, and I'm going to assume that the equation just factorizes as a product of two linear equations over the rationals. I don't need to do this, otherwise, but it just gets a little bit more complicated to describe, so I'll turn it into the most familiar discussion by assuming this. So this is the same as saying that there are two rational points at infinity when you complete the conic. In that case, the existence of solutions is not an issue. The rational points of curve just become isomorphic to Q star, the non-zero rational numbers, and same for all the local places. So here, the existence isn't an issue, but nevertheless, it still makes sense to ask how you locate the global points inside the adelic points. Right? This question is still with us, even in this simplified setting. And so a point of view which may look rather odd if you haven't thought about it this way before, but which I think is rather important, is that this is the question that's actually answered by class field theory. You see, what does class field theory do? Class field theory gives you these reciprocity maps. It defines for you a map from these ideals of Q or any number field to an abelian Galois group, where this G abelian is the Galois group of the maximal abelian extension of Q, which, as you know, is just a field generated by all nth roots of unity, all roots of unity. And the reciprocity map is a map of this sort. It goes from the restricted direct product of all the QVs to this Galois group. So, from the point of view of this map, what does Artin's reciprocity law say? It just says that the global points we're interested in is actually inside the kernel of this map. So this is, I think, a view of the reciprocity law which isn't emphasized enough. That is, what it's really doing from this point of view, it's really giving you a defining equation for the global points inside the local points. For the algebraic variety GM. So it really is, becomes a theorem of Diophantine geometry. It's just the Diophantine geometry of GM. So there are many things you can comment on regarding this point of view. So I mentioned this to a number of people once, and they said this is a very weird way of looking at the reciprocity law, but it's intentional because I really think this is an essential viewpoint. Also, from this point of view, it's very important to phrase the reciprocity law in the idyllic language. If you use the classical language of generalized ideal classes and so forth, you can't quite phrase it in this form. So the point is, let me read. I forgot if I have a slide about it. So from this point of view, so Artin's reciprocity law. Oops, sorry. is just Diophantine geometry of GM. It gives you a defining equation for the global points of GM inside the adelic points. Except the equation is slightly odd. It's an equation with values in a group rather than an algebraic equation with values in a field or anything like that. So my goal for a while has been to formulate a non-abelian reciprocity law of this sort from this point of view. As you know, many people mean many different things by non-abelian reciprocity. The most standard interpretation is the Langlands program, which is of course very important, but that's not the only thing one might mean by such a thing. So in particular, what I'm claiming here is that one should try to do Diophantine geometry for other varieties in this manner. That is to say, you can start with a rather general Diophantine equation, and you would like to understand the set of rational points, and you'd like to do it, as Rika mentioned earlier, by putting it inside the adelic points, which has a more general analytic structure in addition to the arithmetic geometric structure. But then try to define a non-abelian reciprocity map.
Can you go back one slide?
Sure, yeah.
So this map is zero. Is this actually exact?
No, unfortunately not. That's a very good question.
Right. How far does it really give you the equation?
That's a very good question. So, as you know, when you're over a number field, the real components give you a problem in actually formulating precisely what they say, what the image is. So, Andreas's question is, what's the difference between? Of course, it's inside the zero set of the reciprocity law, reciprocity map, but it's not equal. And so one has to work with that a little bit. So there are things you can do. For example, if you periodically complete this map suitably, you can get it to be equal, for example. The other interesting case is if you're doing this all over function fields rather than over a number field, then it's actually equal. So there you get a precise defining equation for global points inside local points in the function field case. So there are many things surrounding that. And that's a very good question to ask. But I'm going to be somewhat vague about it right now, because nevertheless this gives you interesting information about this. So in case there are some students here, I also want to emphasize one more thing about this reciprocity law. I pointed out already that in order to look at it from this point of view, it's important to have the idyllic formulation of class field theory. So this is one reason to do that, if you haven't appreciated that fully yet. But another thing is that, you see, when you first learn about p-adding numbers and so forth, sometimes people encourage this view that these are completely different completions. That somehow you start out with the rational numbers, you can take the real completions, you can take the p-adic completion, and sometimes you get this impression that when you complete, you move to a completely different universe in each case. But if you look at it from the point of view of Galois theory or class field theory, that's not the case at all, of course, because all the different completions sit inside the Galois group. They map to the Galois group and they interact. And an expression for the way they interact is the reciprocity law. So one should de-emphasize often enough the fact that these completions are somehow different. They actually come together inside the Galois group. Right. So the program then would be to start with a general Diophantine equation and try to formulate a reciprocity law that gives you defining equations for the global points inside the local points. Another way is to take a slightly dual viewpoint. So I'm not going to emphasize this today, but this is something that is sometimes easier to make concrete. The dual view would be to not focus so much on the reciprocity map, but instead think about defining functions on this target, whatever it is, in such a way that whenever you have a function here, you can pull it back to a function on the local points that annihilates the global points. So that's another view of the same thing, which is sometimes more useful. So and when you do it this way, of course, you might end up with very explicit formula for functions that annihilate global points. So this is the dual viewpoint. So once again, what's the key point? In some sense, what I would like to do is to do class field theory with coefficients in arbitrary variety x, in such a way that you generalize class field theory, which has coefficients in Gn. And this turns out to be essentially possible. So let me set up the notation a little bit. I forgot what I wrote here. Yeah. So I wanted to describe today how this go. Sorry, I suddenly forgot the order of these slides, so I may have to search a little bit. So I'm going to describe for you what one does here. Sorry, okay. Yeah. Yeah, sorry, I think I got the slides a little bit mixed up. But this is okay as well. So what we're going to do is I'm going to show you how to define such a non-abelian reciprocity map. Yeah? I wanted to put this later because I wanted to spare you as little of the technical language as possible, but let's just do it. So I'll denote now by pi1 with superscript m the pro-m's tau fundamental group of a variety, yeah? Where pro-m is some finite set of primes. So this is the maximal quotient of the étale fundamental group arising from finite quotients that are all, whose orders are divisible only by primes in M. And I denote by this with the superscript n the lower central series, where I'm normalizing it in such a way that for any group, if I write G1n, this is the whole group, and then inside here is G2, which is the commutator subgroup, and so forth. And since this is topological, you'll also take completions, closures of the commutator subgroups. The S sub m is a finite set of primes such that the action of the Galois group on this fundamental group factors through this restricted ramification extension. So I'll explain that also on the side. So when I write Q sub S sub m, this means the maximal extension of Q unramified outside S sub m. So I wrote this. I should explain that it always such exists. That is, if you're given this fundamental group, the Galois action on the fundamental group always factors through some restricted ramification quotient like this, where we have to take, for example, it suffices to take Sm to be all the primes. So I should have said this in order to say this more precisely. For the moment, I should have assumed that X is smooth projective. It's a smooth projective already. I forgot to write that. Or in general, I just have to assume this. So in that case, you can take S to be the set of primes of bad reduction together with the set of primes that divide M. So if you do that, the action of the Galois group on the fundamental group actually factors through this restricted ramification quotient. Now there are some technical conditions necessary, which I'm going to skip for a moment. So these are actually, in a way, these are reasonably mild conditions that are often satisfied, for example, for hyperbolic curves. But anyways, I'll go back, return to this later if we want to discuss this in more detail. But let me state what the reciprocity law is. So here's what one does. So starting from the adelic points of a variety, what we can do is define a filtration. We denote by xa sub 1 the whole thing, then that will contain as a subset xa sub 2, xa sub 3, and so forth. And then for each of these, there's a reciprocity map to some profinite abelian groups with the property that at each stage, the next level is actually the kernel of the previous reciprocity map. So this is the way it's defined. So this is somewhat different from the way I formulated the desire, so to speak, the ideal reciprocity map. But what I can do at the moment is define an iterative sequence of reciprocity map. Subject essentially on any variety, subject to some conditions on Galois cohomology, the slide I skipped earlier, but which one can often check to be satisfied. So let me say again, on the adelic points of a variety, I'm going to define an iterative sequence of reciprocity map, which in this way define a filtration on the adelic points. So we can visualize it this way as well. So this is the first reciprocity map defined on all the points. And on its kernel, we define the second reciprocity map. And on the kernel of that, we define the third reciprocity map and so forth. Obviously, I'm not stating here that there are anything like group homomorphisms or anything. That's the difference from the usual reciprocity, because these aren't groups, these are just sets. These here are groups, but we're only viewing them as pointed sets in some way, and not really as groups. So when I talk about the kernel, I just mean the inverse image of the base point, of the origin considered as a base point. So this is the way the reciprocity map is organized. But then, so let's suppose I denote by x a sub infinity the intersection of all these kernels as I run over all the I. So this is the analog of the kernel of the reciprocity map for GM, except here we need infinitely many of them. Then the theorem is that in fact the global points lie inside all the kernels. So this is the non-abelian reciprocity law. So, subject to the conditions that on cohomology that I've omitted, what you get is the following non-abelian reciprocity law, that the global points are killed by all of these reciprocity maps. So I don't know how much detail I should provide about this theorem, but maybe one thing I should do is tell you the definition of these GNs. These are the targets of the reciprocity map. So that is, it's a little bit complicated, but you use Galois cohomology, you apply it to the dual of these associated graded pieces of the lower central series, and then dualize again. And I think I always get confused about topological group homology, but I think what it is just, with the correct definition, is probably just a group homology of this module. But because I felt a little bit uncertain about that, I did a double dual. And to just say a word for the moment about the definition, the reciprocity maps themselves are defined using global splittings of torsors and an iterative application of portotate duality. And in order to make this precise, I need these conditions that on various Galois cohomology that I omitted earlier. So what is this condition? So let me say just briefly, just to give you a flavor of what's involved. You need that H0 of, so inside, in other words, that each of these associated graded pieces for these quotients of pi 1 have no invariance under the Galois group. This is a very mild condition, it's almost always satisfied. Now, but there's also a condition on first Galois cohomology, which is saying that suitable localization is injective. For example, this condition will always be satisfied for P1 minus 3 points. That's already an interesting case to consider. So you get a non-abelian reciprocity map for involving the global points of P1 minus 3 points. I didn't emphasize that, but one could also do this at the S integral level rather than for all rational points, which is probably the more interesting thing for P1 minus 3 point. So one can check that these conditions are satisfied for many hyperbolic curves. So subject to that, you get a defining equation for the rational points on this variety X, given by, well, a sequence of defining equations, because it's annihilated by all the reciprocity maps. So the rest I'll write a little bit. Yeah. Now, one thing, by the way, which is a little bit misleading about this theorem, is that it is possible that this x sub x a sub infinity is everything. This reciprocity map is not necessarily non-trivial. So that's a remark. So here's a warning. Okay. Proving that x sub I is non-trivial for some I is rather hard in general. Yes, in general, I don't know how to prove this, but it is implied. Well, there are some situations where you can just prove it directly, but it's also amusing to note that this fact is actually implied by, say, some standard conjectures in the theory of motives. Mixed motives. So, for example, parts of Bloch-Hatter conjectures or Fontane-Mazer conjectures. So you could ask, it might be a little bit mysterious, what does this have to do with this reciprocity map? So you see, the non-triviality of the reciprocity map has to do with bounding Galois cohomology in some way. So for example, proving that some localization maps are injective, and one can use, say, these kind of theorems. So the parts of these conjectures that are necessary are all those parts that tell you that certain parts of Galois cohomology entirely come from geometry. So there are parts of these conjectures that take that form. Like for the Fontane-Mazer conjecture, for example, you might define something like H1 sub G Galois cohomology with coefficients in some Galois representation coming from motives, where I say this is a positive weight representation. So motivic and adaptive weight motivic representation. In that case, the Fontane-Mazer conjecture will say that everything in here is also motivic. So if W is a positive weight motivic representation, then this conjecture says that this G refers to a condition on the local Galois group at P, saying that it's crystalline or drum or something like this, depending on how strong you want to make it. The Fontane-Mazer conjecture will then say that everything inside this H1 is also motivic. It's a linear combination of mixed motives that are extensions of the trivial motive by Q. And the Bloch-Hatter conjecture has a component that has the same form, where by motivic, you replace motivic by coming from K-theory in a very explicit way. So then, once you know things like this, you can use this to show that H1 is zero in certain circumstances. And this is the kind of thing that when some global H1 is zero, or when some global localization map is injective, it allows you to actually produce non-trivial reciprocity maps here, non-trivial components in this reciprocity map. So I think it's reasonable to expect that these rect I are non-trivial in general. And another remark, which is maybe the more interesting one, is that, so here's another proposition. This is actually quite easy. Is that if reg I is non-trivial for some I, then what you get is that xq, sorry, let me state this just for curves. So let's say x over q is a curve. Just to be safe, I don't think I need this, but to be safe, I'll assume that it's smooth projective, of genus at least 2. In that case, if some reciprocity map is non-trivial, then this RQ, XQ is finite. So, in other words, you get a faulting theorem from simply the non-triviality of one of these reciprocity maps. And the idea behind this is, so the general idea, I've spoken about this many times at many conferences, right? That's why I'm being slightly vague about this. But the general idea is that you look at the P component, or QP component, examine the QP component. QP component for some P of the reciprocity map, some P of good reduction. Then the fact that this equation SQ lies inside the kernel of the ith reciprocity map. So this leads to the fact that XQ inside XQP is annihilated, is in the zero set of a p-adic analytic function, something called the p-adic Coleman function. That's arising as, which is simply an iterated integral of algebraic differential forms. So, and one knows, so for example, p-adic polylogarithms or elliptic polylogarithms and all such things are the kind of functions that arise here. And what you get is that when one of these reciprocity maps are non-trivial, by projecting to the P component, you can get that equation to translate into the statement that the global points are annihilated by an iterated integral. And this automatically gives you finiteness because of the local property of these iterated integrals. These iterated integrals have the nature that locally they are given by non-trivial convergent power series in every residue disk of the curve, and these have only finitely many zeros. So somehow, a general idea, so as I said, this isn't a proof of faulting theorem in general, although you can use this to prove a faulting theorem in some cases. So this condition is what's hard to verify in general. Yeah? But for example, you can verify this statement is true. Say, in a lot of cases, interesting cases, for example, that family I wrote, these generalized Fermat curve examples I wrote at the beginning. For these, for example, you can check that some ith reciprocity map is non-trivial. Yeah? So you can prove finiteness of points on those kind of curves using the reciprocity law. So it's just a consequence of a reciprocity law. So that's possibly an interesting formulation. But in general, I can't say that one proves it in general, but nevertheless, it feels like it's a reasonable approach to understanding how these rational points sit inside p-adic points or adelic points. Now,
question. So what goes wrong with elliptic curves?
Well, what goes wrong with elliptic? Well, But it's still true, except that in the elliptic curve case, there's only R1, there's no Ri. All the Ri's become trivial except for I equals 1. That is for elliptic curve itself. When you when you do an elliptic curve minus a point, you'll get higher reciprocity maps for that as well. That gives you control of integral points in that case. Yeah? But if you take the elliptic curve itself, there's only R1. And in that case, Ri being non-trivial, R1 being non-trivial does imply finiteness, but that's only in the rank 0 case. Yeah. So it won't be, R1 will be trivial as soon as you have positive rank. So it's slightly a weak conclusion that you draw. It's not that anything is wrong, but it's just the conclusion is weak.
If you take other point, does this give you Siegel's theorem?
That's right. Yeah, it will give you Siegel's theorem in general for affine cards. That's right. But also, by the way, but the R1 case is slightly also interesting, because in that case, the kind of mathematics, you can directly prove that R1 is trivial, is non-trivial in some cases, even for elliptic curves. No? And this is more or less the method that inspired this general theorem and machinery. But that process of showing that R1 is trivial, is non-trivial, and getting the finiteness of rational points in those circumstances is the whole machinery of Euler systems. Which also, and so the R1 will be non-trivial exactly in the case that the L function doesn't vanish at 1. And so therefore will also give you the predicted finiteness of points. So that's also a very interesting case. But it's all this way of phrasing it is sort of unnecessary in that case. But it does inspire the whole thing. And you should think about this question, this issue of proving the non-triviality of reciprocity map as being a kind of higher analog of the machinery of Euler systems. But that's what's hard to get to work. That's why I can't prove this in general. But nevertheless, when it does work, you get the rational points, the global points, as the zero set of p-adic iterated integrals, which is a very pleasant fact. But nevertheless, even in those cases, the thing that's really missing, that I'm still struggling with, is an explicit reciprocity law. So that's kind of missing. So the thing that should be proved in addition to all these things, whether or not one can prove the non-triviality of this Ri in general, is one should ask. So, we could write that as a desideratum. It is an explicit reciprocity law. That is to say, as you know, in the classical reciprocity law, so there's this general art in reciprocity law, but it's very hard to really apply it to anything until you can somehow describe the reciprocity map in some very explicit way. For example, by constructing a collection of units on which you describe the local reciprocity law and see how it makes the different primes interact and so forth. And that seems to be what's very hard to do in general, essentially, essentially because somehow, you know, I don't need so much of this anymore, so I get it. Oh, that's okay. Let's just get rid of it. I don't think unless there's going to be questions about it. No. That's all. Just leave it alone. So, yeah. So that's the main thing that I'd like to prove. Some kind of explicit reciprocity law involving this non-abelian reciprocity maps. But the difficulty is that what really comes into play is this non-abelian cohomology. So you get various things like 그래요? 그게 문제인가요? 아이고, 이게 배터리가 그렇게 많이 들어갈 것 같지가 않은데. Oh, sorry about that. We're out of my computer ran out of battery, it seems. Right. Okay. So I'll have to say this just in words. But eventually, In order to describe this process, I guess unfortunately I lost the slide that contained the a brief discussion of the splittings that you need to construct these maps from. But eventually, even though the targets of the reciprocity maps are just involve just this Galois cohomology of this sort, these associated graded pieces. So these are the things that go into the targets of the reciprocity map or various duals. And this is just an abelian Galois module. And I guess I get rid of the restricted ramification eventually as well by going to various limits. But nevertheless, in the process of constructing the reciprocity map, one needs to consider non-abelian cohomology. So eventually, if you want to give a very explicit description of reciprocity maps, you need ways to construct elements. You need to construct elements inside non-abelian cohomology, whose targets you can describe in the under the reciprocity map in some explicit manner. This is, very roughly speaking, the nature of general explicit reciprocity laws in classical class field theory as well. You construct explicit elements whose images you can describe under the reciprocity map and use it, well, to give a general description by constructing enough elements. But this seems to be something that's very hard in non-abelian cohomology. So you'd be trying to, philosophically speaking, you'd be trying to construct things that are like non-abelian Euler systems. And this seems to be very hard. And so that's where I'm stuck, more or less. But nevertheless, I hope this gives some flavor. Without, I'm sorry that I gave a very superficial description, but I hope it gives some flavor of the kind of thing one might be interested in and get the kind of profit that may be had by looking at Diophantine geometry from the point of view of reciprocity laws. Yeah, so I guess I'll just stop there today since the computer gave up. Thank you.